Let's see. Yes. All right, so we'll take this, be a little bit loose about this here. As for some people that were here on last Saturday, we discussed some of what Lyndon Larouche is getting at in a paper he wrote back in 2005 called Vernadsky and Dirichlet's Principle, where he discusses a certain breakthrough he had made in understanding Vernadsky's use of a principle that was used by Riemann in his investigation of abelian functions, which is the use of something known as Dirichlet's principle. Now, Dirichlet was a mathematician who was a teacher of Riemann's, who actually, I think he took over the chair of mathematics at Göttingen after Gauss had retired, and taught a series of lectures which then inspired Riemann, who then himself later took that same position. But what Larouche is getting at is he's looking at, as was brought up and mentioned earlier in the briefing, of looking at these different phase spaces, the living, the non-living, and the cognitive phase spaces of existence in the universe, and trying to understand how do you define or sort of generate a thought object about these various types of phase spaces, which a thought object which in fact corresponds to the reality of these phase spaces. So what he looked at was the way that Vernadsky had defined what he calls the biosphere, which is the region of existence on Earth, which penetrates a certain number of meters into the ground, into the soil, into the depths of the ocean, and also penetrates a certain number of meters into the atmosphere, a certain kind of envelope, so to speak, of the Earth, where life is able to carry out its activity, where the products that exist within that space are products which are fossils or are effects which are created by the principle of life. And Larouche had an insight that, in fact, what Vernadsky was doing was attempting to define the characteristics of that space by the principle itself. That the principle was what was bounding and then defining, characterizing the quality or type of action that could occur within that envelope. And so he references Dirichlet's principle, which is a mathematics principle, a geometric principle, whereby you're trying to investigate a geometric space, not from the standpoint of pairwise interactions. Adrian, dude, just get a chair, man. You have like a habit of somehow imposing your presence into virtually everything that occurs in this room. But, so, what we're going to look at initially is we'll read through some of this paper by Riemann on abelian functions. And, with some discussion about, just give you a sense of what Riemann was doing and try to give people some kind of quasi-working idea of what this Dirichlet principle is, or what this theory of abelian functions is. And then we'll look at that. Then we'll look at some of these quotes from Vernadsky that Larouche uses, and hopefully you'll start to see what Lynn is getting at. And then from there, we'll take a look at a very specific example based off of a recent paper that's been circulating on the development of solid continents at the hands of photosynthesis, as a sort of a pedagogical example of the role of, say, the biosphere in determining activity on Earth. So, why don't we just kind of take a little look through here. All right. Is there anybody who would like to can read something scientific with a certain zeal. You can't see that? There's plenty of seats up here. You can move forward. No, I'm serious. There are literally like 5, 6 seats up here. All right, can you see that? Yeah. Okay. All right, can someone want to read this aloud? Huh? Any takers? Anyone want to read this aloud? All right.
Riemann, Theory of Abelian Functions, Crowell's Journal, Volume 54, 1857. Completed first draft. Preliminaries. 1. General hypotheses and methods for the study of functions of unbounded variables. The intent of presenting to readers of the Journal of Mathematics my studies on diverse transcendentals, and in particular also on abelian functions, inspires in me the desire to avoid repetition, to reunite in the commencement in a preliminary exposition the general principles which will be the point of departure for my treatment of the subject. For the independent variable I will take, at first, the geometric representation of Gauss, well known today, in which a complex variable, z equals x plus iy, is regarded as a point on the infinite plane with rectangular coordinates, x and y. I will designate complex numbers, and the points which represent them, by the same letters. I will consider as a function of x plus yi any magnitude w, which varies with this quantity while always satisfying the equation I dw over dx equals dw over dy.
Just real quick, let me see.
Paradox.
So we have to do this thing.
You gotta tilt the
This thing
Yeah.
back like this.
Yeah.
All right. Let's see. Well, if we do it like this. Okay. So we can maybe just for people who are totally unfamiliar with some of this. Okay, so just initially he's talking about, when he talks about a function, how do you call it, function z equals x plus yi.
IY.
What he's talking about there is, and there's obviously a lot more that goes into this, but Gauss developed an idea of complex numbers, where you're looking at a number which when looked at on a plane, or on a surface, instead of the typical notion of numbers along some kind of linear line of positive and negative, let's say we had this was our origin point, our point 0. We would understand numbers moving not only left to right, but up and down. That, in a sense, you're defining positions on this surface from the standpoint of the amount vertically and horizontally that gets you to that position. So for example, if this was 0, we go over +1, +2, and then up 1, which is in our I direction. So you've sort of got a situation where you've got, this is our unit circle of radius 1. You have 1 minus 1, the square root of -1, and negative the square root of -1. And these became generally characterized as I. So this is equal to I, this is equal to negative I. So to talk about a number Z or position Z, this is our position Z, it would be equal to 2 plus I1, or 1I. So it would be positive 2 and positive 1 in the I direction. So in this case, Z would be equal to 2 plus I. And so in general, we're going to be looking at surfaces where all positions on the surface are being defined as complex functions, where every position will be understood as some relationship in the x and y direction on that surface. And so when he talks about z equal to x plus yi, is regarded as a point on the infinite plane with rectangular coordinates x and y. That's what he's talking about. And when he talks about a function, he's talking about where w is a function of x plus iy, where the change of the function, and this dw, this is a partial derivative. So your partial derivative of your function relative to x in the multiplied by I to make it equal here, because here your I is with your y. So we're multiplying I on this side to compensate for the I on this side. But the general idea is that your the change of your function relative in your x direction is equal to the change of your function relative to the y direction, which there's a lot more to be said at that, but it's indicating what is sometimes known as a kind of a harmonic relationship, where your rates of change in two orthogonal directions are equal to each other. And this is one of the characteristics of a minimal surface, which Riemann developed the idea that all Gaussian surfaces are minimal surfaces, meaning that the rates of change in the two orthogonal directions are equal to each other. And they don't always have this same kind of, they're not always straight up and down lines. There's a whole series of different kinds of functions which are of this quality. Maybe just to give people a picture of one. Like this here, what you're looking at here is what's known as a complex transformation of a grid of the type we just described, where everything is these orthogonal lines being squared. So where every position on this surface is being squared, which is a function of some doubling of the angular relationship to the origin, right? Because this has some kind of angular relationship where the angle is being doubled and the length or the radius is being squared in length. So every position, not only known in terms of a x and y, but can also be known as an angle and a radius. And so every position is being squared where the angle is doubled, the radius is squared, and we're getting a transformed surface. But even though this is seemingly a very different surface from the one we start with, it still has the relationship that these positions, that the two different types of curves moving in perpendicular relationship to each other, these would, in this case, it's sets of perpendicular parabolas, that they still maintain this idea, this principle of rates of where their rates of change in the two perpendicular directions are equal to each other. So it's one of the characteristics of what's sometimes known as a harmonic surface or a harmonic function. So just and if there's any questions, you can ask now or write them down for later. And don't worry, we'll be through this part soon enough.
Should we continue?
Yeah.
Alright, so I'll just read that sentence before.
Yeah.
I will consider as a function of x plus yi any magnitude w, which varies with this quantity, while always satisfying the equation I times dw over dx equals dw over dy, without hypothesizing an expression for w in terms of x and y. As a consequence of this differential equation, by virtue of a known theorem, the magnitude w is representable by a series proceeding following. Right. The magnitude w is representable by a series proceeding following the integral powers of z minus a of the form n equals infinity, or it's a sum of from 0 to infinity, a sub n times z minus a to the nth power, provided that in the neighborhood of a it admits everywhere of one determined value, varying continuously with z, and that this possibility of representation holds up to a distance from a, which is to say a value of modulus z minus a, where a discontinuity is found. With the aid of considerations which rest upon the principles With the aid of considerations which rest upon the principles of the method of undetermined coefficients, we recognize that the coefficients a sub n are completely determined when w is given along a finite line from a, however small it may be. In uniting these two propositions, one can be easily assured of the exactitude of this theorem. A function of x plus yi, which is given in a portion of the xy plane, can be prolonged beyond it in a continuous manner in only one way.
All right, so there's a lot in there that it's not necessary to get into. If you'll see the footnote, this kind of wild-looking equation up there with this summation sign up there at the top. Oh, but Jason, I think it's a footnote that Jason put in there, who translated this, that this is called a Taylor expansion. And this is something that people that were at the cadre school may remember. We looked at some of this with sort of a way of taking something which is discontinuous algebraically and using a infinite algebraic series to approximate a discontinuous point. But this isn't going to be as important to the overall idea of what we'll get into today.
Now, let us conceive of the function we are considering as not determined by any expressions or analytic equations containing z, but rather by the fact that the value of the function is given in a portion of the z plane with arbitrary boundaries, and that it is extended in a continuous manner by means of the differential of the partial differential equation I times dw over dx equals dw over dy. This extension, performed by the power of the preceding propositions, is completely determined if it is performed not along pure lines, for then the application of a differential equation is impossible, but along surface bands of finite width. Now, according to the nature of the extended function, it either will or will not always have the same value for the same value of z, whatever may be the path along which this extension was performed. In the first case, I will name it uniform. It would then be perfectly determined for any value of z and will never be discontinuous along a line. In the second case, where it is called multiform, attention must be given to certain points on the z-plane to understand the development of the function, points around which the function extends into another. For example, the point a for the function the logarithm of z minus a is such a point.
And he'll get into this now. And I'll explain some of this in a minute.
Let us conceive a line drawn from this point a. We can, in the vicinity of a, choose the value of the function, such that the function varies in a continuous manner, except along this line. But on the two sides of this line, it takes different values, the value on the negative side being 2 pi I greater than the value on the positive side. The extension of the function beyond one of the sides of this line, for example the negative side, then the region located on the other side, gives therefore evidently a different function than that which appeared formerly, and which, in the case envisaged here, exceeds everywhere this latter by 2 pi I. To simplify the designations of these relations, we will name the various extensions of one function on the same portion of the z-plane the branches of this function, and a point from which one branch of the function extends into another branch point of the function. Wherever there is no branching, the function is considered as monodrome or uniform.
All right, maybe just discuss that briefly. All right, so what is 2 pi?
You want an answer or?
Yeah, a circle. 2 pi is basically 360 degrees. So, for example, he's looking at, because here's one of the things we had with Gauss, is that Gauss developed, for example, with this, let's go back to this image we looked at before. Right, he developed this idea of looking at algebraic functions geometrically, where you could take an algebraic function and understand it as a transformation in what's known as the complex domain, where you're using really trigonometric functions, where the positions on a surface have a certain trigonometric relationship to each other. And so you get these kinds of transformations. But one of the problems that you had with Gauss, or what was sort of an ambiguity, was that for every position, say in your infinite plane, before you have a transformation, you have an infinite number of positions, right? Extending, right, in a positive and negative direction, infinite, negative infinity, positive infinity, positive infinity I, and negative infinity I. So you have this infinitely extended plane. And now you're going to square this surface. But what occurs when you square is that, just like in any kind of algebraic equation, just take a simplest one. Take like x squared equals 4. What's x?
2.
Okay. Only, could it be something other than 2?
Negative
Negative 2. Right, so that has two answers. Which Gauss showed was, okay, whenever we take this, we transform the surface, that, well, negative 2 on our first, our square, our plane, our infinite plane, 2 and negative 2 now correspond to one position on our transformed plane. And so it was so there's a certain ambiguity there. Like, okay, well, here's a position on this plane, but there's two sort of solutions that satisfy that location. And so what Riemann was able to do in sort of taking this idea of the complex domain of Gauss was to elevate it to say, okay, if we introduce a new kind of idea into these functions, we can now represent those two solutions as two different locations on a plane which is multi-leafed. So for example, you see here that can you kind of see how one sheet is kind of moving underneath another one? So even though it looks like whenever it's all said and done you have one infinite plane, it actually has two sheets to it. I think maybe there's something that kind of like this. And that in general, any movement along one of these lines, which would be sort of your least action pathways along this surface, which is another element of Dirichlet's principle. Dirichlet was looking at things like magnetic fields, electromagnetic potentials, and showing that you had certain kind of, that a minimum function could be generated to represent the pathways of action within that space. And that those pathways would always be of a minimum quality, a minimum character. You know, much like I think Freddie and maybe Frank, you're going to do a class in a couple weeks on some of the work that they did in Leesburg on Fermat. And Fermat made a breakthrough showing that light always travels in a pathway of least time, that it always takes a minimal pathway. And this became a general idea developed by Leibniz of a principle of least action, that action in the universe will always take a kind of a least action pathway, whether measured in time or space-time or what have you, that there's a certain kind of ontological efficiency in the universe. And so this idea was extended by people like Dirichlet and then Riemann in investigating real physical phenomena, like, say, the space that's created through, say, a magnetic potential. So any kind of movement along this surface is going to be continuous. You can set up a function which describes a continuous movement around this surface, except, for example, here, along what's known as the branch point, or the branch point and the branch cut. There, a continuous movement, is going to put you 360 degrees in the I direction away from where you had just departed. That it's not absolutely continuous, but there's a certain discontinuity, which in fact is which really defines the characteristic of the surface. And so this is what he's talking about when he talks about branch points and branch cuts. That as you moved along, say you're on the bottom of the surface, you're moving in a continuous way, at a certain point you're going to cross the branch point and you're going to be 2 pi I. The function is now going to have a solution which is 2 pi I different from just the moment before. And so that describes the characteristic of the function just before and just after the so-called branch cut. But in doing this, what Riemann's able to do is to develop a way of describing in a knowable way a function which has discontinuities embedded in it. That instead of just saying, okay, we have a function which at certain points becomes discontinuous, he's saying, okay, we can have a function which is continuous up to a point, which then becomes discontinuous, but in such a way that we can know how and why it becomes discontinuous, and then becomes continuous again, so to speak, on the other side of the singularity. And so it actually represented a real fundamental breakthrough for mathematics. We were able to describe functions, where now functions, of course, were not simply just curves, right? Like at the cadre school, when we were looking at some of the stuff of Leibniz. Leibniz was just looking at curves, like a parabola or an exponential curve or something like this, and saying, okay, y is a function of x squared, or y is a function of e to the x, where your change in the y direction was a function of e to the x. As you moved in the x direction, your change in the y direction was e to the x, e to the power of whatever algebraic movement you had in the x direction. Or with the parabola, it was, if your x was 2, your y was 2 squared. If your x was 3, your y was 3 squared, etc. Now our functions are no longer just looking at lines. Our functions are describing surfaces. So we're looking at something where the functions are projections into a space, a two-dimensional space, which represent projections from either three-dimensional space or even higher. And you're looking at the way that higher spaces project onto a two-dimensional surface. And now what Riemann is looking at is a way to describe surfaces which ostensibly are continuous to a certain extent, but which also are capable of containing or capable of representing singularities within what is otherwise a continuous surface or a continuous function. And so he's developing a method by which we can describe and understand such kinds of functions. And what he really gets at, and we'll see him say it directly, is that it's in fact the singularities which define the characteristic of the surface. That, for example, in our squared surface here, it's the point about which the whole surface is transforming, which is defining or determining the characteristic of the surface as a whole. So that it's not so important that we're able to describe every moment on the surface, but that we can know that because processes in the universe have a kind of a least action characteristic to them, a lawful process in the universe will manifest itself, say in terms of a surface representation, as a least action kind of space, that really all we need to know are what are the singularities which are defining the characteristic of that space, and then know that the space as a whole is going to be some kind of least action relationship between those singularities. And so this is the kind of thing that he's getting at when he's talking about these branch points, of looking at what's the singularity. Like here you can see the point in the middle, it's not moving, it's not changing. It would sort of, in a sense, it would be the singularity of this function around which everything else changes. And then along a cut of this thing, say along one of the lines here, which you can see here, this would move you as you moved around this thing, around the singularity. You would then cross a branch cut that would then move you up to the next leaf of the surface. And so you're sort of able to carry out a continuous, so that you can carry out a continuous action, but you're passing through a discontinuity. And so he's developing a way in which you can represent that. On the one hand, you're carrying out a continuous action, but you're doing it in such a way that you're bridging discontinuities in the process. And you'll see this obviously, people have become more and more steeped in the kind of thing Lynn's looking at. In the So You Wish to Learn Economics, people may remember he discusses this thing of the discrete and the continuous manifold, where you're looking at, one way of thinking about that is you've got these different kind of discrete phenomena in history, say in terms of technology, when you're moving from, say, burning of fossil fuels to the burning of oil, to then the use of nuclear power, then on to fusion power. These are certain singularities within the process, the upward development of man, But at the same time, you can also understand that as a continuous process. There's a certain continuous process of the upward progress of mankind, of physical economy, but which is characterized by the singularities along the way, which define the choice of pathways that move you from one singularity moment to the next. And that can be understood as a continuous function. So this kind of thing he's getting at here.
Hey, Cody,
Yeah.
could you explain again what was the breakthrough that Riemann made?
Well, he's developing a way of being able to represent this kind of a function. And we talk about a function here, we're not simply talking about a function in the way it's first described in mathematics. Usually a function is often, like we talk about with the parabola, where we'd say y is a function of x squared, where your position, your y height on your graph is a function of where you are along the x-axis squared. So you would say y is a function of x squared. Now we've incorporated the breakthroughs of Gauss, of his discovery of the complex domain, which is the idea of the development of a surface, in effect, which is more of a medium where physical principles or physical action are projected onto, but in a lawful way, such that what's presented in that complex space, the complex domain, is a lawful representation of the kind of action that's occurring in real physical space, so to speak, in the domain of principles. So we're looking at functions from the standpoint of the characteristics of change on these complex surfaces. So now we're not just simply looking at lines, we're looking at surfaces, where the entire surface is a function of some kind of principle of change. The characteristic of the surface is a function of some principle of change. And that what Riemann was able to do was to develop a means of using these complex surfaces as a way to, in effect, make intelligible functions which have discontinuities in them. Because any kind of, like we've looked at before, any kind of attempt to describe or to communicate an idea about a transcendental, for example, right? A number which is representative of a higher principle, a higher order principle, is discontinuous. Takes on a discontinuous characteristic relative to the kind of algebraic function you're using or attempting to use to describe it. Right? You have a certain kind of infinity point or what have you. And so he's developing a way to make intelligible, through the use of the complex domain and complex functions, a way of representing a discontinuous process. To say, can we make a process which is discontinuous at certain points in the function intelligible to the human mind? And so he's developing a means to do that. Where you're developing, in effect, a certain continuous functions or continuous surfaces which contain discontinuous moments. But where you're able to sort of use the discontinuities to move in a continuous way from one position to another on the surface.
Was that niche animation an example of that?
Yeah, that was sort of an animation of a kind of surface which has that characteristic. Where there's certain, on that leaf, there are certain positions on that leaf where if you're trying to describe as a function the movement around that surface, it would become discontinuous. Because you're passing, say, from the bottom leaf up to the second leaf, the top leaf. Algebraically, you can't describe that in a continuous way. But you can represent it using these complex functions as a continuous process, but a continuous process which has moments of discontinuity in it. You know, like the kind of thing you have in an economic process. Right? Humanity, the development of human economies it's a continuous process, but it has singular moments within it, has discontinuous moments in it. You can't ever look at the way human beings are functioning at any moment and say that we can project that activity indefinitely into the future. Right? It's constantly going to have to reach certain moments of transcendental change in order to progress, to keep moving up. But the whole process is knowable as a continuous process, right? As Lynn has demonstrated in his understanding of physical economy. But it's a continuous process which is characterized by those discontinuities. And in fact, it's those discontinuities which are determining the pathways of action which are going to move you from one discontinuity or one singularity to the next. And so you'll see some of this as we move here. You want to keep reading there, Mike?
Sure. Where were we? To simplify?
Yeah, I think so.
To simplify the designations of these relations, we will name the various extensions of one function on the same portion of the z-plane the branches of this function, and a point from which one branch of the function extends into another branch point of the function. Wherever there is no branching, the function is considered a monodrome or uniform.
I just have a quick question back on what you were just saying. So the Gaussian surface doesn't show those discontinuities, like with the 2 and the -2?
Right, they're there, but with the Gaussian surface, you would have effectively say on the squared surface, you would have two solutions or two functions which would describe one position on the surface. Whereas with Riemann, he's saying no, actually those two positions lie on two different leafs of a surface. Like whenever you just sort of square the surface, like we talked about, 2 and -2 are going to end up in they're going to end up in what would be position 4 on our squared surface. Whereas with Riemann, those two positions would be on different, what he calls leafs
Yeah, I'm just trying
of
to
a
remember
surface.
when we actually made those Gaussian surfaces. I thought there were 2 different positions on there for the plus and the -2.
Yeah, those are surfaces of just algebraic equations. Here we're looking at taking a surface itself and squaring the whole surface. Yeah, but they're related in a certain way. Yeah, I mean, yeah.
Want to move it up a little?
Oh yeah.
A branch of a function of multiple independent variables, z, s, t, and so on, is uniform in the vicinity of a determined system of values, z equals a, s equals b, t equals c, and so on, when to all combinations of values up to a finite distance from this one, which is to say when a determined finite magnitude of moduli z minus a, s minus b, or t minus c, and so on, correspond a determined value of this branch of the function, varying in a continuous manner with the variables. Branch points, or points around which one branch extends into another, are formed for a function of multiple variables by all the values of the independent variables satisfying an equation among these variables. There exists an equation written in terms of the variables whose solutions give the branch points.
Right. Does that make sense what he's saying there? Saying that you can, there's an equation which gives you, which, like he says here, gives you the definite solutions which correspond to these branch points. So that you can generate an equation such that solutions to that equation are the branch points for the function. And so by that, the function itself would be defined by the branch points. Instead of just solutions to an arbitrary algebraic equation, the solutions to our new type of equation are the branch points of our complex function.
Okay. Following a known theorem, of which we have spoken earlier, the property of a function being uniform comes down to the question of its susceptibility of being developed by a positive or negative integral powers of... Okay, let me try it.
Sorry.
Okay. I'll just try that again. Following a known theorem, of which we have spoken earlier, the property of a function being uniform comes down to the question of its susceptibility of being developed by a positive or negative integral powers of growing variables. And the branching of a function comes down to the impossibility of such a development. But it does not seem useful to express properties that are independent of the mode of representation by the help of characters that depend on an explicit determined form of the expression of the function. In several studies, notably in the study of algebraic and abelian functions, it will be useful to represent the mode of branching of a multiform function in the following geometric fashion. Let us conceive a surface extended on the xy plane and coinciding with it, with the plane, or if you like, an infinitely thin body extended on the plane, which stretches as far and only as far as the function is given for the plane. When the function is extended, this surface will thus be extended just as far. In a region of the plane where two or more extensions of this function are found, the surface will be double or multiple. It will be composed of two or more leaves, each corresponding to a branch of the function. Around a branch point of the function, one leaf of the surface will extend into another leaf, and in such a way that, in the vicinity of this point, the surface can be regarded as like a helicoid, whose axis is perpendicular to the xy plane in this point, and with infinitely small screw threading. But when the function, after z has made several rotations around the branch point, takes again its initial value, as for example, z minus a to the m over n, m and n being relatively prime, after n rotations around a, one will have to suppose then that the leaf above the surface joins the lower leaf in passing through the rest of the leaves. The multiform function has, for each branch point, one single determined value, and can thus be regarded as a perfectly determined function of location at a point on this surface.
Cody?
Yeah.
What's a helicoid?
It's like a corkscrew type thing. So yeah, so like this picture is a tube. This kind of thing he's describing. This one has two leaves. Each of these has a leaf, where they're connected at the center here. So right there, there's one position which only corresponds to one point, which will be your branch point, where these two things are connected. And then as you move around this thing a certain number of times, at a certain point, you're then going to pass back down to the bottom leaf again. Does that make sense? And then, in fact, the space between this leaf and this leaf is infinitely small. So I said you've got this heliocoid, which sort of the thing which connects all of them, but which is infinitely, they say, has an infinitely small angle or something, pitch to it. But as you move around this surface, you'd be moving right in a continuous way. You keep crossing through a branch cut. Every time you cross through a branch cut, you move up to up to the next leaf of the surface until you reach the top leaf. Then when you cross that branch point again, it's going to bring you down to the bottom of the surface again. So you got to think about this as a mental object at a certain level, because this idea does exist as one uniform idea, as one singular idea, but which has various discontinuities within it. Right? When analyzed as a function, as an algebraic function, it's wrought with singularities. It's not continuous, but yet it can be understood and represented as a singular idea, as one unity. Now let's look at one other element here. Okay. Here's where he starts to get into some of, the way he develops these surfaces. You want to keep reading, Mike, or you want to pass the baton?
From where?
Just from one. So all that, there's a couple sections of introductory section, and now this is the beginning of his development of the whole thing. So I think the whole paper is about 50 pages or so.
Let S be the root of an irreducible equation of degree n, whose coefficients are integral functions of z of degree m. To each value of z correspond n values of S, which vary with z continuously throughout, where they are not infinite. One represents, therefore, according to section 3, the method of branching of this function by the in the z-plane extended unbounded surface T, such that it is in each part of the plane n-fold, and S is then a single-valued function of position in this surface. An unbounded surface can be considered as a surface whose boundary is infinity, or as a closed surface, and it is from this point of view that we will regard the surface T, such that the value z equals infinity corresponds to one point on each of the leaves, unless z equals infinity is a branch point.
All right, so does anyone see what he's saying there? He's talking about the infinity becomes z equals infinity, becomes a point on the surface. This is the kind of thing you get whenever you map a plane onto a sphere. Some people are familiar with this. If you do it, say, in the opposite direction, if you want to map every position of this sphere onto a plane, effectively you're doing it by projecting, say, as a light source from the top of the sphere down through any position on the sphere down to where it hits the plane. And so you can see that the blue lines here, they get extended into these blue lines, and your red lines around this way get projected as circles on your plane. The distancing of the circles from each other are going to have an exponential growth to them, an exponential growth function to them. And so you're going to extend this plane out to infinity. I mean, you can imagine that as you're moving up and projecting higher up here, the angle, say from the side,
Stand on a chair.
huh?
Just stand on a chair.
I'm just going to pull it back down in a minute. So if you were to take just one, say, crosscut of this thing, one circular crosscut, and you're projecting a light source from the top through these positions onto a plane. You can see the way that positions on the sphere are being projected, mapped onto the plane. Right, as you move up with your light source and you're sort of sweeping up this way and you're projecting each position onto the plane, that the distancing between your positions, so to speak, say equal distancing and angle, are going to produce exponential distancing on the plane. You can get this plane that's going to keep going out, growing further and further and further. The pole, the top position, where's that going to extend to? Where's that map to?
Every direction.
Huh?
Every direction.
Yeah, when does it stop? When does it hit the plane? Does it ever?
Depends on the space it's in. Does it?
Yeah, it just goes to infinity, right? So, conversely, if you then just took the plane and mapped each of these points onto the sphere, you could, for every point on the plane, you could find a corresponding point on the sphere. And your infinite point, would actually have a location on the sphere at the pole. And so this is what he gets at whenever he says this idea that that the value, an unbound surface can be considered as a surface whose boundary is infinity. An unbound surface can be considered as a surface whose boundary is infinity, or as a closed surface. And it is from this point of view that we regard the surface T such that the value z equals infinity corresponds to one point on each of the leaves, unless z equals infinity is a branch point. So if you have a surface where the leaves are now envelopes of the sphere, your various infinities of each of the leaves would correspond to stacking of positions at the pole, unless in fact the pole itself was a branch point, at which then it would be just one position with one value, one singular value, which connected all the various n dimensions of the sphere.
Is a sphere a closed surface?
Yeah, it's sometimes known as like a self-bounded surface. You want to keep reading there, Mike?
I had a question.
Yeah.
What is the object with which higher mathematics is concerned with or directed towards? Is it like space, thought, generation, as like expressed in chemistry or biology, or even on the astro level, like with the birth of stars? Kepler used trig to find the orbits, like a surveyor uses trig to find or to make maps. So does higher mathematics give us like a way to measure those type of phenomena?
Yeah. Yeah. I mean, these things with Riemann, he's unique in that he develops a lot of what some might think of as sort of abstract higher mathematics, but he applies this method to real physical processes. But what he's developing is a means of lawful representation of actual physical space-time. Because as we looked at, and this is just sort of a thumbnail sketch, but you know, if you look at from the standpoint of Kusa and then with Kepler, you do have the development and discovery of a transcendental principle, the idea of a universal principle, something which is a determining characteristic of change in the universe. Right, with Kepler's discovery of gravitation as a principle which is acting at every moment in our solar system, in our universe, what have you, to determine a certain characteristic of relationships in the universe. And that every principle is of that quality, like life. Life is a principle which defines or determines a quality of change or a characteristic of relationship in the space which is being affected by the principle of life. Now what Riemann's doing is he's developing a means by which you can start to investigate not simply just relationships of position, not simply just relationships of number, but looking at relationships of transcendentals. Or in other words, looking at relationships of principles. How is a space-time determined as a function of the relationship amongst some set of principles? And now here he's doing this somewhat of an abstracted way and looking at transcendentals. But from the standpoint of this arc from Kusa to Kepler to Leibniz to Gauss, etc., we actually come to see that the transcendental is not simply just a number, but it's a number which characterizes an efficient principle in the universe. Right? The transcendental is indicative of a place, or is indicative of an attempt to try to use a lower order mathematics like algebra to define a higher order process, like we saw with the exponential. When you try to describe the exponential or the circle from the standpoint of algebra, it becomes discontinuous. Your algebraic function is not capable of containing the idea of the circle or the idea of the exponential curve, right, which will express itself as something which is undefinable. You know, it either the function becomes infinite or it becomes zero, or it takes on a ambiguous quality to it. And so now he's looking at it and saying, okay, well, let's take these singularities or these discontinuities and start to look at how do discontinuities relate to each other. Let's look at the way that a space is being shaped as a function of the relationship amongst these discontinuities.
And mathematics give us the tools to approach the questions like the Timaeus or
Yeah.
like Philo's on creation.
You ever read Larouche's paper, the Principle of Powers? Or no, not the Principle of Powers. Power to Prosper. In there, he says something to the effect that Riemann's development of abelian functions is the highest expression of an understanding of God in the universe. So Lynn clearly thinks so.
Well then, how is higher math? What's like the best method for teaching higher mathematics, or should I say, what's the best method in which one can inspire or spark the flame? There we go. What is the best method in which an individual begins to spark the flame of another to really pursue a knowledge of higher mathematics?
That's where the economics comes in. I mean, ultimately, it comes from wanting to, at least from my standpoint, it comes from a want to more fully understand Larouche's own breakthroughs in physical economy. Like, as physical economy, ultimately, we're dealing with of developing a method for the successive higher order development of human beings, of the human potential. And so if really your zeal is for the development of the human potential, well then that really the highest form of that is physical economy as understood and developed by Larouche. And so if you really want to fully understand and be able to represent his discovery, communicate his discovery, you're going to have to develop a means of not just comprehending things like the abelian functions and even higher order functions than that, but then starting to develop our pedagogical powers to communicate those discoveries and ideas. You know, which is a lot of what, I mean, that's Bruce's whole intention really in developing the whole Riemann for anti-dummies. And ultimately, it's the reason for the whole basement work, is to then take what had been done in the movement and what Bruce had done and really just flesh the thing out fully and just really make it a intelligible and communicable process. But we'll get into some of that.
I got one last question. I hope I'm not ruining the class.
Well, you're taking a lot of time, but I mean, you might want to save it till the end.
All right, good idea.
Oh, you want to keep reading there, Mike?
We had every rational function.
Yeah.
Every rational function of S and Z clearly is equally a uniform function of position on the surface T, and possesses therefore the same method of branching as the function S. We will see below that the reciprocal is also true. The integration of such a function gives a function whose different extensions for the same portion of the surface T differ only by constants, since its derivative for the same point of surface takes always the same value. Such a system of equal branching, algebraic functions, and integrals of these functions will be the first object of our study. But in lieu of starting with the expressions for these functions, we will define them by their discontinuities in applying Dirichlet's principle.
So that's how he starts that section. Just go to this footnote just to clear up something here. So what he talked about in the very beginning there, in describing the kind of functions that will get at these surfaces. Those who remember the 1799 paper, here you have something which is what became known as the Big Mama equation, where your unknown variable is your x. And so you'd have this equation equals whatever. And so you'd have various, you'd have m number of solutions to this equation. And you'd have, you could apply Pascal's triangle, etc., to find out the various coefficients. Now here, what you've got, and now so you'd have a surface. So you'd be able to develop a surface where that surface would be characterized by the solutions to that algebraic equation, so to speak, where the sine and cosine functions crossed each other in the projection on the complex plane. Here we're looking at one where not only are you looking at something of this form, but where the coefficients themselves are functions. So that in effect, every position of the complex surface, every position is not simply just a position in terms of an x, y, I position, but every position is itself a function of, some algebraic type, or, becomes, it's where then you start to find where it becomes discontinuous, etc. And so now you're dealing with something which is, in a sense, transcendentally higher than just simply an algebraic surface. So that's something people should obviously take a look at. But in general, the key point to be gleaned from that, just as a thought, is this last sentence, where he says, such a system of equal branching algebraic functions and integrals of these functions will be the first object of our study. But in lieu of starting with the expressions for these functions, we will define them by their discontinuities in applying Dirichlet's principle. And so that's the crux of what Lynn really is getting at in looking at Dirichlet's principle as it applies to Vernadsky's investigation of the biosphere, and saying that Vernadsky applies the same kind of method in looking at the biosphere, of saying that we're going to use the principle, in this case the discontinuity between the abiotic and the biotic is the principle of life. That there's a certain discontinuity between the two phase spaces. That discontinuity is that distinguishing characteristic which is a living process, or a living action, or an effect of a living process, as distinct from an abiotic phos, or an abiotic process. And then conversely, then even above that is your noetic. So let me see here, take a look here at this. So here's here's some of the quotes that Lynn takes from Vernadsky. It says these are things that he read in this Vernadsky paper which struck him as being proof that Vernadsky had some working understanding of this Riemannian conception of Dirichlet's principle. If not in totality, if not in absolute form, then at least in some approximation. So he says, and this is Vernadsky, quote, a great part of our work is connected with a study not of the atoms themselves, but of chemical elements, of isotopic mixtures. In purely chemical processes, all of the isotopes of the same element are manifest in a similar way. Hence, while we remain within the field of purely chemical processes, the chemical element may be identified with the atom, as it is in the case of the periodic system of elements. On this, the whole chemistry is based. Proceeding from this general statement, it has been possible to show by the work of our laboratory that the atomic composition of organisms, plants and animals, is as characteristic a feature as their morphological form or physiological structure, as their appearance and internal structures. An organism does not show a passive attitude towards the chemical medium. It actively creates atomic composition. It tends to choose, consciously or unconsciously, the chemical elements necessary for life. But as life presents a field of dynamic equilibria, it reflects, both in its composition and in its form, the different physico-chemical properties of the medium. These variations, however, do not change their average, little varying expression. For life, the field of life, the biosphere, is not a structureless, casual Earth's surface. The face of the planet upon which life originated, according to E. Seuss, of the cosmetic medium of life, according to C.L. Bernard, the biosphere is not only the face of the Earth and not a cosmic. The biosphere is not only the face of the Earth and not a cosmic medium. The Earth's shell has a strictly definite composition and structure, determining and controlling all the phenomena that take place within it. The phenomena of life included. It is morphologically distinct but closely related to the general structure of the planet. A number of the most characteristic and important geological phenomena established such a character of the biosphere with certainty. Its chemical composition, as well as all the other features of its structure, is not casual and is most immediately related to the structure and time of the planet and determines the form of life observed. The biosphere is not an amorphous nature, a structureless part of the space-time in which biological phenomena are studied and established independently of it. It has a definite structure, changing in time according to definite laws. This is to be taken in consideration in all the scientific deductions and the logic of natural science in the first place, and this is not done. The nature of the naturalist is not the biosphere. It is something very definite. Is only the biosphere. It is something very definite and delimited. If this structure is called a mechanism, it would be a special, very peculiar mechanism, a continuously changing mechanism, a dynamic equilibrium, never reaching a state strictly identical in the past and in the future. At every moment of the past and of the future time, the equilibrium is different, but closely resembling it. It contains so many components, so many parameters, so many independent variables, that no strict and precise return of some state in its previous form is possible. An idea of it may be given by comparing it to the dynamic equilibrium of the living organism itself. In this sense, it is more convenient to speak of the organized state rather than of the mechanism of the biosphere. Life is continuously and immutably connected with the biosphere. It is inseparable from the latter materially and energetically. The living organisms are connected with the biosphere through their nutrition, breathing, reproduction, and metabolism. This connection may be precisely and fully expressed quantitatively by the migration of atoms from the biosphere to the living organism and back again. The biogenic migration of atoms. The more energetic the biogenic migration of the atoms, the more intense is life. It is nearly dying out or hardly flickering in the last phases of life, the importance of which in the organized state has not yet been evaluated, but should not be overlooked. The biogenic migration of atoms compromises the whole of the biosphere and is the fundamental natural phenomenon characteristic of it. So that's important. The biogenic migration of atoms comprises the whole of the biosphere and is the fundamental natural phenomena characteristic of it. So, let's see here. The property of the living substances having nothing equal to it in the substance of the planet, not only at the given moment, but also in the aspect of geological time, completely distinguishes it from any other earthly substance and makes a distinction between the living and inert substance of the planet quite sharp. The more so that all the living is derived from the living. The connection between the living and the inert substances of the biosphere is indissoluble and material within geological time, of the order of 1 milliard of years, and is maintained exclusively by the biogenic migration of atoms. Abiogenesis, that is life out of non-life, is not known in any form of its manifestation. Practically, the naturalist cannot overlook in his work this empirically precise deduction from a scientific observation of nature, even if he does not agree with it due to his religious or philosophically religious premises. The whole work of the laboratory is based on such a structure of the biosphere, on the existence of an impassable, sharp, materially energetical boundary between the living and the inert substance. The whole work of the laboratory is based on such a structure of the biosphere, on the existence of an impassable, sharp, materially energetical boundary between the living and the inert substance. It is necessary to dwell on this point, since it appears to me that in this question there is a vagueness of thought which impedes scientific work. We do not proceed here beyond exact empiric observation, the deductions from which are obligatory for the scientist and as a matter of fact for everyone. It is on this observation that he not only can but must base his work. These deductions may possibly be explained differently, but in the form of empirical generalization, they are to be taken into consideration in science, for an empiric generalization is neither a scientific theory, nor a scientific hypothesis, nor else a working hypothesis. This generalized expression of scientifically established facts is logically as obligatory as the scientific facts themselves, if it has been logically correctly formulated. The sharp, material, energetic distinction of the living organism in the biosphere, of the living substance of the biosphere, from any other substance of the biosphere, penetrates the whole field of phenomena studied in biogeochemistry. And so Lynn takes off from that point. But, I mean, hopefully some of that's clear in what he's getting at, that he is saying that there is definitely this very sharp distinction between any kind of living process and a non-living process. That, in fact, the biosphere is defined and determined as distinct from the abiotic and then conversely from the noetic by a very sharp distinction, which he characterizes by this biogenic migration of atoms, which is things like, what all of you are doing right now, hopefully, is breathing, right? There's a certain exchange of material, oxygen, nitrogen, all the elements of the air, which are not living in and of themselves, but are moving into a living process are then at that point part of a living action, right? Just as all the material that makes any of us up, right? There is no material which is by definition living in and of itself, but it's the exchange, it's the flow of material in and out of living processes, and the rate at which that occurs, and the sort of the direction of that occurrence, which he defines as the biosphere. And so the rate, or the sort of the amount of that kind of flow of material, is what's going to determine sort of the life of the system. And you see this, I mean, this is the characteristic of evolution. That as evolution has progressed over time, the tendency has been to move towards more energetic forms of life. Mammals relative to cold-blooded animals have a much higher metabolic rate. Their rate of exchange of material between their living form and the outside biosphere is much higher than that of cold-blooded animals. And as you see, mammals are they came along later in the evolutionary process. And so that's what you're looking at, is that you got within then the biosphere itself, is you've had this upwardly moving, developing process of higher energy states within the biosphere itself. So, this is something Lynn looks at, and he starts to draw certain kinds of correlations between this and, say, economics. Where if you say, what's really an economic process? Right, an economic process is not simply, say, respiration, etc., the biogenic migration of atoms as such, but it is sort of the noetic flow of materials. Now, beyond, say, not counting, say, just the discourse of ideas through culture, etc., which we can get to, but just look at what constitutes an economy, a healthy economy. Right? Say it's the flow of things like steel, iron ores. Right? The fact that we mine iron ores, we condense them, we refine them, we then shape them to build structures, to build factories, what have you. Or we organize them in higher forms, to say from simple locomotives to then maglev trains. Food, right? The growing of food, the concentration of solar energy in such a way that it's now something which is consumable by human beings. And so you see that in a noetic process, but what's the process of organizing that? Right? That is really the issue of human economy. Is how do you actually organize the concentration and flow of materials over the face of the earth? This then gets us some of what you're asking about, Moses, in terms of why things like these abelian functions, etc., become important. Because ultimately that's what this is the idea of, maybe just to take an example of this in the biosphere, from this paper that's circulating now on the role of photosynthesis in creating the continents. That, all indications are that upwards of about 4 billion years ago, the planet Earth really didn't have solid continents. It was pretty much characterized by relatively shallow, homogeneous oceans, and you get certain kind of mass would form, disintegrate, but there was no idea of continents because of the material structure of what are called like these basalts, etc. They broke down easy. They're flimsy. They just weren't capable of sustaining themselves as solid structures on the face of the earth. Now, as this theory goes, as it's been developed, was that around that time is really whenever we started to see photosynthesis, or the most popular form of photosynthesis, which is the combination of of water with carbon dioxide and the breaking it down to produce oxygen and CH4, I think it is. Yeah, no, this is like, anyways, we can find it. We can read the paper. It's like CH4. I can't remember what the exact name of that element is. Something, yeah. We could look it up afterwards. But the general point was that you had a massive, through photosynthesis, you had a massive saturation of oxygen into the atmosphere, and then its absorption through certain kinds of convection flows, etc., into the mantle, into the material substrate of planet Earth. Now what this led to was you would create this bonding between the oxygen and iron. So you'd have this FeO, ferrous oxide, which what that did is that as the base salt of the mantle was being built up and would break down, etc., you get exposure. Whereas before, when you didn't have this level of oxygen was not an abundant element in the atmosphere, you just have a constant reconstituting of the same kind of crust, a non-rigid, very malleable kind of crust. But now, with the emergence and abundance of oxygen, and the fact that oxygen was then binding with the iron portion of the base salt, it was then resulting in then the formation of granite. And what that meant was that now you had a material that was solid in form. One that was more buoyant, was sort of lighter than the previous material, and so it was in a sense kind of float atop the heavier mantle. And it was also rigid. It would form into more rigid, hard structures, and that became the continents. I mean, our continents that we're on one right now are largely made of granite. That's sort of the main mineral composition of the continents is granite. Now, if you think the process through, granite, without that we couldn't have continents. Without continents you wouldn't have land sustaining animals, climates. Without continents you wouldn't have the kind of processes through other kinds of mantle flows that led to the formation of mountains, which then created diversity of climates through the containing of weather systems, etc. So ultimately you had with photosynthesis and the oxidation of the atmosphere through the formation of continents and all of that, what followed from that, you had this process of evolutionary development where we were moving towards higher forms of animal life, greater diversity of climate. You know, you combine that with the fact that prior to that, like the fact that we have so much water on planet Earth, that's a result of living processes. Right? There's a reason why you don't have the abundance of water on other planets as we do here. It largely has to do with, one, the role of life in producing the abundance of water, the fact that life then created things like the continents, which created the certain kind of atmosphere which is able to trap heat, which is able to create certain convection flows of water through rain, etc. And then now say take that and put that in the context of, say, some of the things we've learned from our investigations of Kepler. You know, like the latter book of Kepler, he talks about things like the precession of the equinoxes and the changes of the movement of the rotation of the ellipse itself. Now it's from things like the tilt of the Earth, the relationship of where the Earth is tilted relative to its position on its ellipse, which then creates different temperature variations on planet Earth. Now, given that most of the continents are in the northern half of the planet, that under right conditions is where you get things like ice ages. Ice ages, though, wouldn't be possible, or only a result of the fact that we've got such abundances of water and the fact that we have things like continents. And so you start to look at the interrelationship between the kind of effects that result from the principle of gravitation combined with the effects that result from the principles of life, and you start to see this kind of development, this anti-entropic development that's been occurring on planet Earth, which is, and then now you want to take that and look at that as it relates to, say, human economies. Because we see on planet Earth we become more and more complex, more and more diverse, that the anti-entropy is increasing naturally. But it's something which is a function of sort of an inherent curvature to space-time. The space-time of gravitation, the space-time of the living principle. But it's not something which is necessarily conscious to the organisms themselves. It's not like the little microorganisms decide, let's get together and start to form continents or something. Right? It was not a self-conscious communicated process amongst them. They're sort of reacting to a certain kind of space, a certain kind of shape of space of living processes. But it's different now whenever you talk about human beings. Right? Human beings conspire. Human beings exist in a higher phase space where consciousness is a characteristic of the phase space. Communication of ideas is a characteristic of the phase space. The way in which we then move beyond, say, the upper limits of anti-entropic development of the biotic is through the conspiring, the self-conscious conspiring of human beings to further increase the anti-entropic characteristics of the planet through the gathering and directing of flows of materials like iron, like radioactive elements for power production, like the channeling of the flows of water. But that then that's an economic process. And that becomes then the subject of physical economy, and that becomes the subject of credit. That's why credit is a unique and profound human discovery. Because credit really is the idea of human beings self-consciously acting to direct the flows of resources and the flows of human activity to an increase in anti-entropy and anti-entropy. Right? That's what real credit is. That's what Hamilton's talking about. Right? How do we, from the standpoint of the future, organize our flow of resources, organize our labor, organize our workforce, organize our education, organize our culture in such a way that we're moving towards an increased density of new discoveries, an increased density of new technologies. We're transforming the face of the earth to the effect of increasing the power of mankind to further be creative. And that's what real credit is. That should be the power of the dollar. I mean, in a healthy economy, your U.S. dollar is backed up by the fact you've got human minds which are conspiring to direct the flow of its people and its resources towards the creation of real material wealth in a sense of industry, infrastructure, education, cultural centers, etc. From that standpoint, that's whenever things like science become truly subjective. Because now it's not, we often talk about science as subjective from the standpoint that, the discoveries are made by human minds. Right? It's not simply an empirical observation which leads to a discovery. You say, okay, science is subjective. It's not simply objective. You're not just a blank slate observing phenomena and then acting as an automaton upon those observed phenomena. So it's subjective. It takes a certain human will, a human act to make those discoveries. But it's also subjective from an even higher standpoint. Because if you think, it's a knowable thing, you can know that in fact the universe has a certain characteristic to it. And this is where you can really start to break down your environmentalists and Malthusians, etc. Is that you can know with scientific certainty that the solar system, the biosphere, has a certain orientation, a directionality to it, a natural characteristic, a natural curvature to it, which is anti-entropic, which is moving towards higher states of order, greater complexity. Life is a honest and truthful thing in this universe. Right? Life is something which the universe desires more of. Right? The universe has been organizing itself to producing more life on planet Earth. Now, from that standpoint, in knowing that, you can know empirically, so to speak, with scientific certainty that that is the characteristic, the directionality of development of our planet and of our solar system. And from a higher standpoint, you can know that the human being is capable of even moving that further, of not only, in effect, harmonizing with that anti-entropic directionality, but moving it in a transcendental way beyond that, in the sense that we're able to produce a quality of anti-entropy which is not capable solely through the principles of life. We're able to increase the power of life by increasing things like the density of plants and things in places like deserts. We can bring life to dead areas. We can increase the density of life in areas which are otherwise relatively sparse. Right? We can bring more fresh water to the continents to increase the power of life on those continents. And we can increase the power of mankind, which is living, but we can also increase the power of creativity and cognition, which is that which is capable of making all of what was previously said possible. And so subjectively, knowing that that is the characteristic of the universe, that must necessarily force one to ask, well, what's my role in all this? Right? Can I now say, can I carry out an honest investigation about what is the reason for human existence? What is the reason for my own individual existence? That's whenever science becomes truly subjective. Because you can know whether or not the way in which you conduct your life, the thoughts which move through your mind, are in harmony with the natural, quote-unquote, curvature of the universe. If not, then you're not living honestly. You're not living according to the intention of your existence, which is your choice, but it's not a very good one. And it's also one which has effects on those which depend upon you making the right choice. Right? Generations yet born cannot choose to guide how you act. They're in effect dependent on you acting appropriately to create the conditions whereby they can realize their creative potential, or afford the opportunity to realize their creative potential. And so that's where we stand in all of this. So I'll end it there and take questions if there are any. And if not, we are free to go. And all of the paper, the abelian functions paper, is, people can find it somewhere.
Probably on the open site.
Yeah, the WLYM
Talking about the power to prosper.
/ Oakland something.
Oh no, the abelian function papers.
Yeah.
Yeah, I got a quick question, man.
The power to prosper one can be found in the Larouche Pub Larouche writings. Also, the Vernadsky and Dirichlet principle. People should read that to start.